Okay, so we have two examples here. There's a cost benefit model. It says a utility company burns coal to generate electricity. The cost of removing P% of the smokestack pollutants is given by this function here for 0 to 100. Again, because it's a percent, you're either removing 0%, you can move up to 100%, but more than likely it's going to be somewhere in between those values. Use a graphing utility to graph the function. You're a member of a state legislature that's considering a law that would require utilities to remove 90% of the pollutants from the smokestacks, where the current law requires 85% removal. Question is, how much additional cost would the utility company incur as a result of the new law? All right, so to graph it, first of all, P is my exit coordinates. So notice when I graphed it, I did 0 to 100. Now I give myself a margin. So I think I did 105 or something on the right, and then I did -10 or -20 or something like that on the left. But I knew it was going to get 0 to 100. What I had no idea was how high I needed to go on the y-axis. I knew it had to be positive because C is not going to be negative, but how much or how large would that cost get? So there's a couple different ways to do this. One is by actually jumping in and figuring out the cost of removing 90 and 85%, and then that gives you an estimate, a couple of numbers to work with. The other thing with Desmos is I started off plugging in, like, I went to my Y maximum and I plugged in 100 and I couldn't see the graph. So then I added on another zero to make it 1,000. Couldn't see the graph. Then I added another zero and another one and another one. And eventually it came out to be, what's this, 1,000,000, I believe, up here. And that's when I finally could see the graph. So Desmos does this thing where it automatically updates as you change the values. So it makes it very nice to do. All right. So what we need to figure out is here for number 2, or part B, is I need to figure out the cost of removing 85% of the pollutants, the cost of removing 90% of the pollutants, and then the difference. Okay, so the question is, how much additional cost would the company incur? So we're just going to go ahead and plug 85 into the function. So the function again is C equals 80,000 P times 100, or divided by 100 minus P. So I get 80,000 times 85 over 100 minus 85, and that comes out to be $453,333. C of 90 would be 80,000 times 90 over 100, take away 90, and that comes out to be 720,000. So how much more of a cost would it incur? So we're going to subtract those values, and I get a $266,667 additional cost just to remove that extra 5%. And so the question, I mean, if you're into politics and everything like that, I mean, part of me says, well, these companies make a boatload of money. What's an additional $250,000? What happens often, and again, this is just what I've heard, I don't know any CEOs, is the company doesn't want to lose that $266,000. So they in turn pass the cost over to the consumers. And so the cost of electricity or whatever they're generating would go up as well. So we need to be careful when we're working with big companies like that. Number 11, something else that's important. For a person with sensitive skin, the amount of time in hours the person can be exposed to sun with minimal burning can be modeled by this function here. And this model is only true for when S is between 0 and 120, where S is what's called the Suncer scale reading, which is based on the level of intensity of UVB rays. So it's ultraviolet. I'm not sure what the B stands for, but rays. So this would be a value that you'd have to be given because we have no idea what this Suncer scale is. So it says find the amounts of time a person with sensitive skin can be exposed to the sun with minimal burning when S is 10, 25, and 100. So for part A, all we're going to do is we're going to evaluate S of 10. And I'm not going to, we just plug 10 in. We get 2.75 hours. We do S of 25, plug 25 in, and we get 1.32 hours. And then we do S of 100, and we get 0.61 hours. So with this, if the S value based on the sensor scale was 100, then someone could spend just over a half an hour outside before they're going to get some serious burn as a result of it. So B, if the model were valid for all S greater than 0, so in other words, if we didn't limit ourselves to being less than 120, what would be the horizontal asymptote of this function? So again, the horizontal asymptote, we look and we see it has the same degree on the top and the bottom. So the horizontal asymptote is going to be that ratio. So it's 0.37 hours. As far as what it would represent, okay, what that means is that as S goes to infinity, time goes to 0.37 hours. Or in English, basically it means this. It doesn't matter how high the intensity is of these ultraviolet rays. Any person with sensitive skin would be able to spend a third of an hour outside with minimal burning. And that's just not true. So, um, so we wouldn't be able to, that's why we have to have that limiting value on there. All right, so those are just a couple of examples. There's nothing, Delta didn't have any application problems, so just I wanted to take a look at them for your benefit. All right, good luck on the Delta math.